Hello, welcome to today's class. In today's class, we will talk about tree search and graph search. Um, in the last class, we talked about the simple problem solving agent, and in that class, we saw that the search operation is one of the important step in this pseudocode because it is this search operation that finds the solution for the problem. So starting from today's class, we will start talking about this search operation, and we will look at different search algorithms. And we will use, for today's class, we will use this route finding algorithm, where our initial state is Arad and our goal state is Bucharest, and we want to find a route. So our initial state is Arad. So this is our current state, and so the search algorithm first check whether our current state is our goal state or not. So that's what the search algorithm should first do. Because it could be that we are already in the goal state. So the search algorithm first checks whether the current state is our goal state. We know that our goal state is Bucharest, and our current state is we are in Arad. So definitely this is not our goal state. So we are not in the goal state. Since we are not in the goal state, we will expand the current state. So what do we mean by expand? Expanding the current state means applying each legal action to the current state and thereby generating a new set of states. If you remember in our in the problem formulation class, we said that there are 5 components in the problem formulation, and in one of the component we specify what are the legal actions in each state. And since the problem formulation is provided as input to the search algorithm, the search algorithm will be able to find what are the legal actions possible at any given state. So if we are not in the goal state, then we will expand the current state, and to expand we have to find out what are the legal actions that are allowed in the current state. In our example, if we are in Arad, then we know from the previous class that the valid actions that are possible in this state are go to Sibiu, go Timisoara, and go Girend. So these are the 3 actions that are possible, and now we will apply all these 3 actions, and that would result in some new states, and these are the new states that we have. So this is the situation after expanding the current state. And here we have 3 leaf nodes. So what is a leaf node? Leaf nodes are those which don't have a children. So Arad is not a leaf node because it has 3 children, whereas Sibiu, Timisoara, and Gerend, they are leaf nodes because they don't have children. The set of all leaf nodes available for expansion at any given point is called the frontier or open list. So all the leaf nodes, they constitute the frontier, the leaf nodes that are available for expansion. So in this case we have 3 leaf nodes, which means in our frontier we have 3 nodes in our open list. So Arad won't be on the frontier, only the leaf nodes will be in the frontier. Now out of these 3 nodes that are in the frontier or open list, we next need to decide which of these 3 states to consider next. Remember, our goal is Bucharest, and now we want to select one of these 3 nodes to consider next. Since we have not explored the 3 yet, so we don't know what is beyond this level, so we may not be knowing which would be the best state to consider next. So which node is selected next for expansion depends on the search strategy. So different search algorithms may apply different search strategy, and based on what search strategy is being used, one of these 3 would get selected. So for example, search algorithm 1 may choose Sibiu, but another algorithm may choose Timisoara. So it depends on what is the search strategy. But the main point is, since we have not explored beyond this level and our goal is Bucharest, we actually don't know which of these 3 may be the best option. Just for explanation purpose, let us assume that the next node that is selected is Sibiu. So now Sibiu becomes our current state. So the first thing we will do is check whether the selected state is our current state or not. Whether the selected state is our goal state or not. Again, we know that our goal is Bucharest and our current state is in Sibiu. So definitely we are not in the goal state. And just like before, if we are not in the goal state, we need to expand the current node. And to expand, we have to consider what are the valid actions that are allowed, and when we apply those valid actions, we will end up with 4 new states, because from Sibiu we can go to Arad, we can go to Făgăraș, we can go to Aradia, or we can go to Râmnicu. So this is how the situation now after expanding our state Sibiu. So in this so in the current situation we now have 6 leaf nodes. So our frontier consists of 6 nodes. The process of expanding nodes on the frontier continues until either a solution is found or there are no more states to expand. So we'll continue this process until we find the solution, our goal state, or we don't have any more states to expand, which means we are not able to find our goal. This tree that we are constructing as the search is progressing is called a search tree. So search tree have the initial state at the root, and the branches are the actions, and the nodes correspond to states in the state space of the problem. So this is the search tree. What is the root of the search tree? Arad, which was actually our initial state. What are the other nodes? These are the states from the state space. We have studied what is state space earlier. And this branch corresponds to the actions that we have taken. So from Arad, the action was go CPU. We ended up in this node. From Arad, and this action was go Timisoara, so we ended up in this node. So these edges or these branches correspond to the actions that we have taken. Go Sibiu, go Timisoara, go Zerind, and so on. Whatever we have explained so far can be summarized in this pseudocode. And this is the pseudocode for the tree search algorithm. And as you can see, the search algorithm always takes a problem as input and it returns a solution. And or if it's not able to find a solution, it will return failure. And this we know already from the last class, where we said the search algorithm takes the problem as input and it returns the solution as a sequence of actions. Okay, now if you look at the body of this pseudocode, what we are doing, we are initializing the frontier using the initial state of the problem. So at the very start, our frontier will be in Arad for the example that we have taken. So frontier will have only one node, and that is in Arad. And now we will perform a loop. We'll continue this loop, and we'll continue this. We'll exit from this loop in two different ways. The first case is when we cannot find a solution, then we will return failure. This is one way we can return from this search algorithm, and we'll exit the loop also. And the other way we can exit this loop and also return from this function is by when we find the goal state, then we'll return the solution. So we can return from this function either as a failure or after we find the goal state, that is, we have found a solution. And this loop continues until one of these two conditions occur. And what are we doing in this loop? We first check whether our frontier is empty or not. If the frontier is empty, that means we don't have any more nodes that we can expand. And since we have not returned from here, it means we did not find a solution, and hence we will return failure. However, if our frontier is not empty, then we will go to the next line where we choose a leaf node and remove it from the frontier. Which leaf node will be removed? It depends on the search strategy of the algorithm. But one of the leaf node will be removed from the frontier, and that leaf node becomes our current state. And on that selected node, first what we do is we check whether the selected node contains a goal state or not. So if the selected node contains a goal state, it means we have reached our goal, which actually means we have found a solution, and hence that solution will be returned. If the node do not contain a goal state, then we need to expand the node, as we have already explained in the previous slides. So if it is not a goal state, we need to expand the node, and whatever new node results, we will add them to the frontier. So that is our tree search algorithm. And if we look at the search tree again, what we can see is that our initial state was Arad, and when we expanded Arad, we generated 3 new nodes. They are CBU, Timisoara, and Gerund. And then we assume that we have the next node that we will select is CBU. And now when we expand CBU, we add 4 new states, and those 4 new states are Arad, Fagaras, Oradia, and Rimniku. And as you can see, these 2 nodes, Arad, they are repeated states. Arad already appeared in the search tree, and it is appearing again here. And this can lead to a problem, because what may happen, we start with Arad, we generate these 3 nodes, and out of these 3 nodes we select CBU, then we expand CBU and we generate these 4 nodes, and out of these 4 nodes we select Arad again, and when we next time we expand Arad again, CBU, Timisoara, and Gerund will get generated, and out of this, and from the frontier, if we again select CBU, it may continue in that way infinitely. So our algorithm may not end, as it may take an infinite path. So the repeated states may make the search tree infinite. So how can we solve this problem? The algorithm that solves it is called the graph search. Again, a search algorithm which takes a problem as input and returns the solution. And what this algorithm does is it maintains something called an explored state. So explored state consists of the nodes that have already been expanded. Initially it is initialized to be empty, and then in the loop, actually everything else is same as tree search except these 3 lines. In the loop, again, if the frontier is empty, we will return failure, just like before in case of tree search. And then if it is not empty, then we'll select a leaf node and remove it from the frontier, and then we check whether the node contains a goal state. If it's a goal state, then we will return the solution. But now before we expand the chosen node, we will add the node to the explored set. To remember that this particular node we have already expanded. So we'll add the selected node to the explored set, and after that we will expand the chosen node, which will result in some new nodes, and now these new nodes will not be added to the frontier automatically. First we will check whether these new nodes are present in the explored set or not, and the new resulting nodes will be added to the frontier only if they are not in the explored set. So only if not in the frontier or explored set, then only the new resulting nodes will be added to the frontier. So not only the explored set, we'll also check in the frontier. And this algorithm is our graph search. So if we again go back to our example, so we start with Arad. Before we expand Arad, we will add Arad to the explored list, and then we generate these 3 new states. Then we will not add these 3 states by default. First we will check whether they are present in the explored set or in the frontier or not. We know that in the explored set we have only Arad and frontier is empty so far. So first we'll check whether CBU is present in the explored set. No, it is not present because in the explored set we only have Arad so far. So CBU will be added to the tree. And then we take Timisoara. We check whether it is present in the explored set. No, explored set consists only of Arad so far. So Timisoara also will be added. Next we check Gerund. Similarly Gerund will be added. And now at the end of this, in our explored set we have Arad, and in our frontier we have these 3 nodes. And then we are assuming that we are out of these 3 nodes we will select CBU. And now when we'll try to expand CBU. Before we expand CBU, we will add CBU to the explored set. So the explored set will now have Arad and CBU. So these 2 nodes has been explored already. And then we will generate these 4 new nodes. However, when we check whether this node Arad is present in the explored set, we'll see that yes, Arad is already present in the explored set. So this will not be added to the tree. And hence we prevent a repeated state from appearing. So this new state, since it is already in the explored set, it will not be added. Whereas the other 3, Phaegarus, is not present in the explored set. It is not present in the frontier, so it will be added. Similarly, Oradia is not present in the explored set. It is not present in the frontier, so it will be added. And similarly, Rimniku is not present in the explored set. It is not present in the frontier, so it will also be added. Only Arad, which is already present in the explored set, will not be added. And this is how we prevent the repeated states, and this is how we can prevent infinite tree. So I think that ends our class today. See you in the next class. Bye.